What's up, engineers? Today we are diving into a problem that looks super simple on the surface, but turns out to be one of the trickiest challenges in computer science, which is graph coloring. And graph coloring is assigning colors so that no two connected nodes have the same color. And this problem shows up everywhere, from scheduling university exams, optimizing frequencies in mobile networks, to resource allocation in big distributed systems, and many more. This type of problems are called NP-complete problems, which take at least exponential time to solve. That means that perfect solution is painfully slow. In practice, these type of problems are solved using algorithms that yield an approximate solution in reasonable time. Such an algorithm is called a heuristic. For that reason, we are going to compare three different approaches. The first one will be backtracking algorithm, which always finds the optimal solution, but can explode in complexity real quick. A greedy algorithm, which is fast but not always smart. And the third one will be a greedy by degree algorithm, which tries to be a little more strategic, heuristic, by handling the most connected nodes first. By the end, you will see why sometimes good enough beats perfect, especially when graphs get bigger and denser. Alright, let's start with the backtracking algorithm, the most brute force of them all, but also the only one that provides the perfect solution to solve graph coloring. So here's the idea. We first try to assign a color to each vertex, one by one. For every choice, we check if the color is valid, meaning none of the neighbors already have it. If it's valid, we move to the next vertex. If we get stuck and there's no valid color left, we backtrack. Basically, we undo the last choice and try a different color. This process keeps repeating until we either color the entire graph successfully or we exhaust all possibilities and realize it's impossible with the given number of colors. In terms of complexity, backtracking is exponential. And the big O is OK to the power of V, where V is the number of vertices and K is the number of colors. So yeah, this solution real quick becomes impractical for larger or denser graphs. And the pseudocode for that will be, or in our case, and how we implement it will be like that. We first initialize the color map and the vertex list, and the color map will be all the already colored numberings, and the vertex list will be a list of all the vertex. The self-coloring function will receive the vertex list 0, which is basically the index of the current vertex in the vertex list, and the max colors, which is the max number of colors that we can try for that particular solution, and the already colored map. Let's jump into code and implement this. The initialize coloring structures function will be like that. We first initialize an empty map and an empty vertex list, and we will iterate on each vertex in the graph, and we will color with -1, which is not a valid color. It's just to start the coloring of all the vertex. We then add this vertex to the vertex list in the same loop, and we then return the colored map and the vertex list. The self-coloring function, on the other hand, it will receive all the vertices, the current index it's in, the maximum allowed colors, which is an int, and the already colored map. And the base case for that will be, well, all vertices are colored. So if the current index is bigger or equal to the length of vertices, we then succeeded. So we can return true, right? So the next step will be the current vertex, which is, well, the current vertex that we will try to color. And for each color from 0 to the maximum number of colors, so yeah, the colors can be just an integer, and we try to see if it's safe to color that specific vertex by passing the current vertex, the color that we are trying to color, which is just an int, and all the colors map. We make a choice. We try to guess here, and on the color map, on the current vertex, we try to assign the color. And then we do a recursive call. That's why we are passing the current vertex on the argument. So we do a recursive call again. We pass the vertices, the current vertex plus 1, the max colors, and the color map. We then return true if it's completes okay, and otherwise we backtrack. We undo the choice, and the color map of current vertex becomes like -1, for example, or uncolored. This is just a pseudocode. And for all the colors, if somehow it didn't succeed on the base case, it will return false if it finishes the loop and didn't reach the base case. So let's implement this in code in Go and see how it works. So yeah, just to give a little overview on the graph. I'm not implementing the graph again because we did that on the past video. However, I'm gonna explain a little bit about how is this structure working. So that's an adjacency list style. So it's very great because I can get any vertex in O of 1 and any neighbor or edges in O of degree. So yeah, it's a really great and optimal solution. It's really easy to work with. So that's why I'm doing this way. This is the new graph function, which returns the interface with an add vertex, add edge, get vertex, get neighbors, and backtrack coloring, and greedy coloring by degree. All of them returns a bool to see if it's possible or not to color. Let's see the add vertex function. We then get the vertex. If the vertex is not it's different from nil, we return the graph because, well, it's an idempotent property, right? So if the vertex already exists, I don't want to add the vertex. We then make a new vertex, and with a new edge, we will add the vertex with that ball and assign this new vertex to that inside our map, inside our graph. So for each one that we do that, we'll increase the length, because this property is will tell us the amount of vertex that we have to add an edge. So the way we are doing that is not a directed graph. So this is undirected graph, which means that if we add a vertex on the 2, we have to add the edge on the from 2. So we first check the from vertex and the to vertex, because both of them, they must exist, right? And we then create the edge that we want with the weight that we are passing here, the destination. So the destination will be the old edge in this case, if it exists already with the current weight. So we're just updating on that case. And if it doesn't exist, we create a new one. So not big deal on that. And we create the edge to the from edge to, and we then assign the to edge and the from edge. The get neighbors function gets all the neighbors on a vertex, so it's not big deal. We just loop on the specific vertex edges and we append to the array and return this thing. So this is are the functions that we are going to implement. Let's start with backtrack coloring. I will start with the helpers functions. So I don't want to use that. So yeah, the first function that I'm gonna make is make the colors, the color map, and the vertices list. The way we can do that is vertices list. So I have done the colored map type before, and we will return the colored map and the list of all the vertices. So the colored map is this, which is basically a map from the vertex value to the color assigned to that specific vertex. So we will start by making a colored map with the length of the graph, so we can assign later on our loop. And a vertices array lies. I'm gonna range on my vertices, on all the vertices I have on my graph, and on the colored map, on that specific value of this vertex, I want to assign -1. So that's assigning that it's not colored yet. And I will then append the vertex value on our slice. Sure. So now the function do color, which will basically tell us if it can be colored, which will actually do the coloring for us. So we first did our basic case, which is all vertices are colored. When will we reach this? So remember, this is a recursive function, and when the vertex index is bigger or equal to the length of the vertices, we return true. So that's our base case. And I want to get the current vertex, which is inside this array. And we then brute force try all available colors on that specific vertex. So we are trying until the maximum number of colors. And yeah, right here, what we need to do is to implement a function called can color. So let's do here. This function will basically check in all the neighbors of this vertex if they already have the current color. So that's why I'm passing the current vertex, the color that it's in, and the colored map. And that's why we need the get neighbors function too. So I'm getting each neighbor value here, and if the current color on that specific neighbor is equal the color we will try to call here. We will call this thing here. So just for you to understand, so that's what we are going to do. We are passing the current vertex, the colored map. This name is not correct, and the colored map. That's what we are doing. So on that case, if it's already colored with that specific color, we then return false. In all cases, we return true. So if it doesn't find any neighbor with that specific color, it will return true. So yeah. Right here, we have to get, we will assign the color on that specific vertex to the color. And we do a recursive call for next vertex. If this function returns a boolean, so on that case, if it works fine, we return a true, and otherwise I want to backtrack the solution. So we will just assign to -1. If for all the colors available, we don't find any solution, we will then return false. right? So this will be how our helper functions will be. And now the backtrack coloring function will be much easier, and this is the hardest of them all. The hardest algorithm of them all is the backtracking solution. So the first thing that we are going to do is to initialize our colored map and get the vertices list, and we then color the do color with the vertices list, and we pass the first index, the maximum amount of numbers, and the colored map. So return true, else we return false. So yeah. One thing that we can do here is to print all the colors if we find the a great solution, if we find a solution. So let's print our colors, and we will pass the colored map. So yeah. Now let's test our solution. So I will initialize a graph first, and this graph will have like 4 vertex. And I will add 2 edges. So let's try to backtrack coloring this graph with 2 colors. And it will be able to color with 4 colors it can too, and with 3 colors it is possible too. Now let's see an example where it can color the graph. So a triangle where all of them are connected, and we will try to color with less colors than it is possible. So I'll make all of them connected to each other, and I will try to color this bad boy. with two colors, which is of course impossible, as you can see. However, with three colors, it is possible. So yeah, let's leave it like that. So that's how you can use the backtrack coloring. Now let's look at something way faster, the greedy algorithm for graph coloring. The strategy here is much simpler. First, we pick an ordering for the vertices. This can be random, alphabetical, by weight, by degree, whatever. The choice actually matters a lot. In this first case, I'm just sorting in increasing order. Then, for each vertex in that order that we chose before, we check its neighbors to see which colors are already taken. We pick the smallest available color that doesn't conflict with any, and we assign it, lock it in, and move on. Here's the efficiency of this heuristic. Unlike backtracking, greedy never goes back to change earlier decisions. It just keeps going. Never goes back, just keeps going. In terms of complexity, this runs in about O to V to the power of square. In the worst case, it's way better than the exponential backtracking. That means it's super fast, even for larger graphs. But here's the trade-off. Greedy doesn't guarantee the optimal solution. Depending on the order of vertices, it might use more colors than necessary. For example, in my test, sometimes it found the perfect number of colors. Other times it ended up wasting one or two extra depending on how big the graph is and how dense it is. The pseudocode for that heuristic will be like that. We initialize a color map and get the vertex list just as the previous backtracking algorithm. We will then sort the vertex list in ascending order, and for each vertex in the vertex list, we will get a color, which will find the first available color by passing the current vertex, the maximum number of colors, and the colored map. If the color is no color available, we return false because we cannot color with the given number of colors, and otherwise we assign to the color on that specific vertex on the colored map. We then print the solution and return true. So let's implement this on code. Let's code this thing up. So yeah, let's first do the helper function, which we'll use. We will need a function to check if the color is available. And we will pass the number of colors that we can color this thing and the colored map. This return an int, which will be the list available color. We get all the neighbors for this specific vertex. We want to get all the forbidden colors. So we can check later on, and this will be a map int to bool, and int of course is the current value. I will then range on this neighbors And if the color exists on our colored map on that for that specific neighbor, first we check if the color exists and the color is not equal to 1, because as we saw on our previous function, when we initialize our colorings map, it will be -1, and we don't want on this case, and the forbidden colors for that will be true. So now I'm gonna range for each num colors. So if it's not on the forbidden colors, we want the first the list not forbidden color, the color that we can use, right? So if it's the first color that it's not forbidden on our map, we will return the color. Otherwise, we return -1. So the first thing, as before, we initialize our colored map and the vertices. I'm gonna range on my vertices, and I want to find the available color, which we can do on our previous made function. We pass the number, the maximum number of colors. We pass the current vertex value and the colored map. So if the available color is -1, as we saw before, it couldn't find an available color. So if the available color is equal to -1, we return false, and otherwise we will color this vertex as this available color, which can be anything. We then print the colors and return true. So yeah, let's test this thing for both our made graphs. Ready, coloring. So let's test with, I'm gonna comment this. So the first case is true, the second one is false, as we can see basically the same thing, because the graph, well, the graph is really small. There was a problem on my greedy coloring that I forgot, which is, well, we do have to sort this thing first, which is the simple heuristic that we were choosing. So sort so this was something that was missing, which won't be so impactful in such a smaller graphs that we have used it, but this is the correct solution. Now let's take the greedy algorithm and make it much smarter. But before doing that, leave it a like below and subscribe to the channel. Also comment down what you want me to bring to the channel. So this variation is called greedy by degree. And the idea is simple. Instead of coloring vertices in a random or fixed order, we prioritize the vertices with the highest degree. In other words, the ones with the most neighbors. And why can this heuristic be so powerful? Because highly connected vertices, which is the ones with most neighbors, they're the most restrictive when it comes to choosing colors. If we color them early, we reduce the changes of conflicts later on, which usually means fewer wasted colors overall, so we can find the optimal solution. We increase our probability of getting the optimal solution. The implementation will be just like the greedy version. The only difference will be the way we order the vertices. The ones with the most neighbors will come first. And just like the simple greedy algorithm, this algorithm has all of v square complexity, still very efficient, but in practice it tends to find colorings that are closer to the optimal solution. Let's dive into the code and implement this solution. Let's implement this thing up. So the first thing we need is this. So it's the first for each of them. And well, we'll need a function to order this thing by degree because we don't have this function yet. So let's make it, and let's call it sort by degree, which will receive all the vertices values on an array and return slice and return and the slice of them order it. And I will use the sort dot slice built-in function because yeah, it's already on the standard library. You can use that to sort slices. So I'm gonna get the first degree, the degree of I, and the degree is the length of the neighbors for that particular vertex, right? And the way we can get that is with the length function. We can get all the neighbors of that specific vertex, so it's the vertices on the I, and the degree of j is the same thing, however, for the j value. We then want to return that in descending order, so which means that the most amount of degrees will come first, and the way we can do that is degree we then return vertices. Yeah. Damn. So yeah. Now it's the same thing as the last one, so no big deal with that. The same thing, and the only thing that's gonna change is how we are ordering things up, and I'm just gonna change that That's it. That's the only thing. Now let's uh test this thing. Because this is such a smaller graph, it won't make a big difference. However, I have done some research on some bigger graphs, and that they are timing to solve the coloring, and we'll talk about that in just a minute. But as you can see, it's just the same thing, but this is smaller graph. So yeah, now let's understand the results of these algorithms. So in my experiments, the simple greedy sometimes wasted an extra color, and on bigger or denser graphs it can waste more colors, and the greedy by degree usually avoided that and matched the optimal solution more often, especially in denser graphs and in bigger graphs too. And of course it can take a little bit more time, and of course it is still a heuristic. There's no guarantee it will always hit the minimum, but in most real world scenarios this small change makes a noticeable difference, and most of the times you just have to use an heuristic. And as you can see, the more the graphs grow, the I mean, it becomes like you can't really use the backtracking solution because it's exponential, it's an NP complete. So in a real world scenario, if you really want the optimal solution for that, you'll most of the cases you will have to run an heuristic over and over again and try with different heuristics to see the best solution possible. That's what happens in most companies with NP complete problems. So that's it for today. Subscribe to the video below, and the code will be below too. Bye.